Welcome back. So far in this part of the course, we discussed the classification of Hamiltonians of gapped non-interacting electrons. Now, real electrons have interactions between them. So if we want to connect what we saw so far to the physical reality, we have to consider the effects of interactions between electrons. Now, let me just mention that real electrons in solids also experience some disorder. The Hamiltonian is never perfectly translationally invariant, and that's another effect we mostly ignored so far. We considered translationally invariant Hamiltonians for simplicity, but we'll just comment that all the classification we saw so far goes through without change, even in the presence of disorder. But this is not necessarily the case once we consider electron-electron interactions. So let's consider the effects of interactions more carefully. So this is the type of Hamiltonian we considered so far. It's a quadratic Hamiltonian of fermions, say electrons. And now we're going to consider higher order terms. So the next order term is going to be a quartic term in the fermionic operators. This corresponds to a two-particle interaction and so forth. We might imagine there are also three-body interactions corresponding to 6 fermionic operators, and so on and so forth. The simplest physical example of this type of term, a quartic interaction, is just the Coulomb interaction, which is the repulsion between two electrons. Okay, and the question we're going to consider is how is the classification of different phases affected if we add to the Hamiltonian this type of term. Okay, so just to put things in context, let's draw a little phase diagram here. So we'll start without interactions. V is equal to 0. And this is the problem we just considered before. So this is, again, non-interacting electrons, a system in some spatial dimension in some symmetry class. And suppose that in this particular symmetry class in spatial dimension, the system is classified according to some invariant, and this invariant allows for different phases, say phase number 1 and a distinct phase number 2. This might be the trivial phase, and that might be the topological phase. And now we vary some kind of parameter in our single particle Hamiltonian, say some parameter in this matrix Tij. Okay, so and as we tune this parameter, we go from phase 1 to phase 2. Now, since these two phases are topologically distinct by assumption, the gap of the system would have to close at some intermediate value, at least at some point, somewhere along this trajectory. So now we're going to add another axis to this phase diagram. Okay, so and this additional axis is going to parameterize the strength of the interactions between electrons. Now, in principle, there are many types of interactions that are possible, but we're going to just parameterize them by the overall strength. And we're going to ask, how is this phase diagram affected? So there are several options. One option is that these two different phases, phase 1 and phase 2, remain distinct from each other even once we turn on interactions between electrons. Okay, so this means that this gap closing point or phase transition point between phase 1 and phase 2 that exists at 0 interactions has to extend into the finite interaction direction. Okay, and this line can never terminate, because if it could terminate, we would be able to go continuously or adiabatically without closing the gap between phase 1 and phase 2. The other option is that maybe the distinction between these two phases is only there in the absence of interactions. So once we turn on interactions, we have another possible axis of motion in phase space, and this allows for an adiabatic path that takes us continuously without closing the gap from phase 1 to phase 2. Okay, and there's a third option, which is maybe the most interesting. Maybe actually in this higher dimensional phase diagram, there are other phases, which are called topologically ordered phases, that are simply inaccessible by non-interacting Hamiltonians. This is a new type of topological phase of matter, which is only accessible in the presence of interactions. Okay, so we've actually seen already in the course an example of such a phase. This is the fractional quantum Hall state. Okay, so the fractional quantum Hall state is a topologically ordered phase which we cannot access from the zero interaction limit. We will have to turn on the interaction by a finite amount before we undergo a phase transition that takes us into this a very interesting phase. Okay, but in this video, we're not going to consider topologically ordered phases. We're only going to ask the question, how does the classification in the zero interaction case affected once we turn on interactions between electrons? And we'll see that the answer is that depending on the symmetry class in the spatial dimension, sometimes interactions modify the classification in a fundamental way, and sometimes they don't. Okay, and in both cases, the answer is interesting, and we'll see as we go along. Okay, so here are some guiding principles. How do we know when interactions cannot change the classification in a fundamental way? Okay, so the first principle we can apply is the following. Whenever a topological phase in the zero interacting limit carries anomalous edge states that we discussed before, okay, edge states that cannot appear standalone in a lower dimensional system, that have to appear as the boundary states of a higher dimensional system, then this implies that this particular phase of matter has to be robust even in the presence of interactions. And let's just discuss a particular example. So we'll consider a two-dimensional Chern insulator again, and this is our 2D Chern insulator that's living on a half plane. It has a boundary which is parallel to the x-axis, and we saw that this phase is characterized by the presence of chiral edge states at the boundary. And these chiral edge states can never appear in a strictly one-dimensional system. They can only appear as the boundary of a two-dimensional phase. Okay, now we want to argue that this by itself already implies that the Chern insulator is actually protected even in the presence of interactions. We cannot, by turning on interactions, we cannot go adiabatically from a Chern insulator that has a non-zero bulk Chern number to a trivial insulator that has zero bulk Chern number. Okay, and the argument is very simple. It's again a proof by contradiction. Suppose that we could actually go adiabatically just by turning on interactions between electrons in the bulk between the topological Chern insulator and the trivial insulator. Okay, so let's just perform that operation in the bulk, but then the entire bulk is essentially like vacuum, but our edge state still remains because we haven't changed the Hamiltonian there, we haven't changed anything there. Okay, and this is a chiral edge state. And a chiral edge state, we just argued, can never appear in a standalone one-dimensional system. So the anomaly of the edge state implies that the bulk is actually protected even in the presence of electron-electron interactions. Okay, and we can go through, there are many examples like that the anomaly of the edge state guarantees that the bulk is actually protected in the presence of electron-electron interactions. Okay, so there are other phases that also have anomalous edge modes. For instance, one and two dimensional topological superconductors in class D. The one-dimensional topological superconductor has Majorana zero modes, as we'll discuss. They have an anomaly, and two-dimensional topological superconductors in class D have chiral edge states, similarly to the 2D Chern insulator. And moreover, also two and three-dimensional topological insulators, class A2, also have anomalous surface states and also are protected and well-defined even in the presence of interactions. Okay? Deriving the topological invariant of the bulk in the presence of interactions may be much more complicated, but the presence of this anomaly at the boundary guarantees that the bulk phase has to be protected. Okay, so let's discuss another principle that would allow us to establish the topological protection of the bulk in the presence of interactions, and this is quantized response. So if the bulk of the system has a response which is quantized, say to some integer, to an external perturbation, then we can argue that this type of quantized response of the many-body system should still be there even if we turn on interactions. And let's consider some examples of this. So let's go back again to the 2D Chern insulator. And we already saw earlier in the course when discussing, say, the 2D quantum Hall effect, that the Hall response or Hall conductivity of such a system is actually quantized in units of e squared over h. Okay, and this is a response of the many-body ground state, and that cannot change if we turn on some interactions. And the reason it cannot change is it's quantized to an integer. So if we change the Hamiltonian slightly actually in an arbitrary way, this integer cannot change by a little bit. It can only jump to another integer, and that can only happen through a phase transition. Okay, it's worth actually to go into this example in slightly more detail. So to that end, let's take our 2D Chern insulator, and rather than on a plane, let's imagine that our 2D Chern insulator is actually living on a finite cylinder. Okay, so this is a cylinder of a finite circumference. It's large but finite. Okay, and through the whole of the cylinder, we can insert an Aronoff-Bohm magnetic flux phi. Okay, and we can change this flux as a function of t. This is as a function of time. This is a very useful theoretical tool to study the a response of the system. So let's consider what happens as we ramp up this flux from 0 to h over e. Okay, because our circumference is finite, the momenta along the circumference are actually quantized. Okay, and they're quantized in units of 2 pi over L, where L is the circumference of the cylinder. And if there's a finite Aronoff-Bohm flux through the cylinder, that simply shifts the quantization condition of momenta along the circumference of the cylinder. Okay, this, if you like, this changes the boundary conditions that the electrons see as they go around the cylinder. So that shifts this integer by an amount, which is phi of t, the flux, in units of phi naught. Okay, so here's our spectrum, say, in the beginning of the process. Time equals 0. Suppose that at time equals 0, our flux is 0. And here's the spectrum of the system. The spectrum is actually quantized. So the allowed momenta are integers times 2 pi over L. Okay, there are two bands, two bulk bands, one with the lower band, say, with Chern number +1, and the upper one with a Chern number -1. And here are the edge states that are connecting the two bands. The states at the edge are discrete because of the finite circumference. And suppose that our Fermi level is right here. Okay, so all the states initially below the Fermi level are filled by electrons, and the states above the Fermi level are empty. Now let's consider what happens as we change the flux. Okay, so now we're going to ramp up the flux from 0 to phi naught as a function of time and follow the ground state of the system adiabatically. So again, here's our Fermi level. Okay, and as we do that, we see that the quantization condition of our momenta is changing in such a way that by the end of the process, the Hamiltonian is essentially the same as it was, because this quantity, phi over phi naught, is just 1. So we just shift the quantization condition, but each momentum has just shifted to the next one during this process. In particular, there's one level which is now above what used to be the Fermi level, which is now full. Okay, so at the corresponding boundary, we've actually added one electron, and we have an excess of charge of plus E. Now, of course, where did this charge come from? It simply came from the other boundary. So there we have a deficiency of charge of minus E. Okay, and it's actually easy to understand physically what happened here. As we applied a time-dependent flux through the cylinder, we applied, by Faraday's law, an electromotive force, which corresponds to an electric field going around the cylinder. And because our system has a quantized Hall conductivity, this electromotive force drives a current in the perpendicular direction. And if you integrate this current over time, you'll get the charge, which is exactly 1e during this process. Okay, I'll leave that as an exercise, but that's not hard to show. So along similar lines, we can actually establish that also a 2D topological insulator has quantized response of a different kind. Okay, so what is this quantized response of a 2D topological insulator that can also be used to argue that this phase is robust in the presence of interactions? So this is a different quantized response. A 2D topological insulator is time reversal invariant, and therefore its whole conductivity is 0, but nevertheless it has quantized response. So let's consider that system also on a cylinder, similar to before. And what we're going to argue is that if we insert an Aronoff-Bohm flux through the cylinder adiabatically as before, and we ramp up this flux not all the way to phi naught, the flux quantum, but only halfway. Okay, so we ramp up the flux from 0 to phi naught over 2. What we'll show is that at the two boundaries of the cylinder, the system will bind Kramer's pairs. So if before threading this flux, we had a unique ground state of the entire system on the cylinder, after threading the flux, we'll actually have a degenerate ground state composed of two Kramer's pairs, one bound to each end of the cylinder. Okay, and this Kramer's pair, the appearance of this Kramer's pair at the boundary is related to the topology of the bulk. Okay, so we can argue this very similarly to what we did before for the Chern insulator. So again, the momenta along the circumference of the cylinder are quantized in these units, and the quantization condition is modified as we change the flux. Here's the spectrum of our cylinder, and now we have a helical edge state. We have two counterpropagating edge modes, and we begin with our Fermi level over here. Okay, so then the states below the Fermi level are all filled, and they of course have to come in Kramer's pairs because the system has time reversal symmetry that squares 2 minus 1. Okay, but now we're going to thread half a flux quantum. We're going to change the flux through the cylinder from 0 to phi naught over 2. During the process, the flux itself breaks time reversal symmetry, but at the end of the process, if a flux of phi naught over 2, or h over 2e, actually preserves time reversal symmetry. An Aronoff-Bohm flux of phi naught over 2 preserves time reversal symmetry. Okay, let's just comment on that. It's a crucial point. So time reversal sends the flux to minus itself, but for an Aronoff-Bohm flux, which is like a phase, the system is only sensitive to this flux modulo integer in units of phi naught. So if we have a flux of a plus phi naught over 2, that's equivalent up to an integer number of phi naughts to minus phi naught over 2. Okay, so a flux of phi naught over 2 doesn't actually break time reversal symmetry. And this is why at the end of this process, the system would go back to being time reversal symmetric. So here's our process, okay, ramping up the flux from 0 to phi naught over 2. And let's examine what happens to the spectrum as we do that. Okay, so the states of the right moving edge mode are moving up in energy, and the state of the left moving edge mode are actually moving down. Okay, so we started from a spectrum that had a unique ground state, but at the end of this process, we actually have two degenerate levels over here, okay, at the same energy, but they're occupied only with a single electron. These two states are actually a Kramer's pair, and there's only one electron occupying these two states. This means that our ground state at the end of the process is actually twofold degenerate. There's a Kramer's pair at the top here, and similarly, there has to be another Kramer's pair at the bottom. Okay? Overall, the system, say, started from an even number of electrons. So overall, there's no global Kramer's degeneracy, but at the two boundaries, we've formed a Kramer's pair after this process of threading half a flux. And this can be thought of as a topological response of the system. And it's a quantized response because a Kramer's pair either appears or doesn't appear as we thread half a flux quantum. Okay, so this is a new type, a different type of quantized response. So now let's discuss yet another example of a quantized response of a topological phase of a even more exotic type. So we'll discuss the case of a one-dimensional topological superconductor that you've seen before in the course. This is the Kitaev chain, and we'll show what is the quantized response in this case. Okay, so just as a quick reminder, we're thinking about a one-dimensional chain of electronic sites. There's a Bogolubov-de Gennes-Hamiltonian which describes this system. On every site we have one electronic state which is which corresponds to the operator psi I and psi I dagger. This is a complex fermion operator, but rather than working with the complex fermion operator, it's more convenient to work with these two operators alpha I and beta I. So these are two Majorana operators. Okay, so every site, a single fermionic state that can be empty or occupied is labeled by two Majorana operators, alpha I and beta I. And our Hamiltonian has two terms in it. Okay, so these Majorana operators satisfy the usual canonical Majorana anti-commutation relations. Okay, and our Hamiltonian has only two terms in it, two types of terms. There's one term that couples beta I to alpha I plus 1, the next site. Okay, so this term is called T. And there's another term which is called T prime, which couples alpha I to beta I within the same unit cell. So this is T prime over here. Okay, so that's it. That's the Hamiltonian of the Kitaev chain. Okay, and this Hamiltonian has a symmetry. In the single particle language, we saw that it's particle hole symmetric. More generally, even in the presence of interactions, this Hamiltonian conserves the parity of the number of electrons in the system. Okay, and this is actually a very fundamental symmetry of the Bogolubov-de Gennes-Hamiltonian of a superconductor. Okay, so in a superconductor, because we have terms of the form psi dagger, the number of electrons is actually not the conserved quantity. It can change, but the parity of the number of electrons is always conserved. Okay, so as long as our system is gapped, we cannot change the number of electrons in the system by 1. We can only change it by an integer number of Cooper pairs. So this means that there's a symmetry, which is e to the I pi times the total number of electrons in our system. Okay, so this is either plus or minus 1, and this commutes with our Hamiltonian. This is in terms of the complex fermions. In terms of the Majorana fermions, it's a simple exercise to just rewrite this conserved quantity, the fermion parity, in terms of alpha I and beta I. And the result is that the fermion parity is simply the product over all sites, I alpha I times beta I. Okay, and you multiply all of these together, you get the total fermion parity of the system. Okay, so now the fermion parity is a symmetry, which means that it has to commute with the Hamiltonian, including any interaction terms we might add. Okay, so now what is the quantized response of the system? So this type of chain can have two different types of boundary conditions. Okay, so as we go, this is a closed chain, no boundaries, but as we go across the entire chain, we can go back to the same degree of freedom or to that degree of freedom times minus 1. Okay, so this means we can think about our chain, which is of length n, as an extended chain, but the site n plus 1 is related to the site n by these two relations. Okay, so the operator alpha n plus 1 has to be either plus or minus times alpha 1. Okay, and this is true for any I and n plus I. And the same must be true for the operator beta. Okay, now why are these actually the only two choices? This is because these are Majorana operators. Okay, so a Majorana operator has to satisfy the Majorana anti-commutation relations. For instance, the operator alpha n plus 1 squared, as any Majorana operator, has to be +1. And this implies that the relation between that Majorana operator and alpha 1 has to be with either with a plus or a minus. It cannot be any other phase. Okay, so now we can ask what happens to the ground state of the system if we compare two chains. One has periodic boundary condition, meaning a plus here, and the other one has anti-periodic boundary conditions. Okay, and the claim would be that the topological phase would actually respond to this change in boundary conditions in a very special way. Okay, so the topological phase, which is the phase where t is larger than t prime. Okay, so in this particular picture, t prime is actually equal to 0, so there's only t. In the case of the topological phase, the ground state with periodic and anti-periodic boundary conditions must have an opposite Fermion parity. Okay, we cannot tell a priori without considering a specific Hamiltonian which is which has an even number and which has an odd number, but we know that the total Fermion parities of the two states have to be opposite. Okay, so this is a quantized property. Okay, so the ground states with even and odd with periodic and anti-periodic boundary conditions can either have the same parity or opposite parity. In the topological phase, they always would have an opposite parity. Okay, so the way to derive this result is just to write the Fermion parity operator as a product over bonds and so forth. Okay, it's a product of beta I and alpha I plus 1. If we multiply all these operators together, we'll get the total Fermion parity operator, which is just a product over all Majorana operators in the system. And if we change the sign of just one bond in the system, that corresponds to going from periodic to anti-periodic boundary conditions, we've only changed the sign in the ground state of one bond, say this particular bond. Okay, that goes from plus to minus over here, and that changes the overall sign of the Fermion parity of the ground state. So this is what happens in the topological phase. We've shown it here explicitly for the case of t prime equals 0, but one can argue that the same happens whenever we're in the same phase. As long as we don't close the gap, this distinction between the Fermion parities of the two states with the two boundary conditions have to be opposite. Okay? In contrast, if we're in the trivial phase, where we can imagine that there's essentially no coupling between different sites at all, t is equal to 0, in this limit, one can easily see that changing the boundary conditions doesn't actually do anything. So this doesn't change the parity of the ground state. And then even if we turn on a weak t between sites and so forth, that's not going to change anything. Okay, so the two states with periodic and anti-periodic boundary conditions, in this case, would have the same Fermion parity. Okay, and let's just mention that changing the boundary conditions in this way, changing the boundary conditions for electrons from periodic to anti-periodic boundary conditions, has a physical meaning. This corresponds to inserting a flux, as we saw before, through the system, a flux which is equal to phi naught over 2, or h over 2e. Inserting that flux through our chain corresponds to switching the boundary conditions for electrons from periodic to anti-periodic. In terms of a superconducting chain, that corresponds to a single superconducting flux quantum, or half a flux quantum for electrons. Okay, now here's another way to understand the protection of the Kitaev chain, or the one-dimensional topological superconductor, class D. Okay, and this is in terms of the anomaly of the edge. So we discussed this phase, and we argued that that phase has a quantized response with periodic boundary conditions. It turns out that this phase also has an anomalous edge state. And all of these facts point together to the fact that this phase is actually protected in the presence of arbitrary electron-electron interactions. Okay, so what is the anomaly that appears at the edge? The edge state should be anomalous in some way. Okay, so to see that, let's reconsider the fermion parity operator again, but now in the case of an open chain rather than a closed chain. Before we considered a ring, now we consider an open segment. And what happens there? Okay, so the total fermion parity operator is still a symmetry of the system. And now we can write the total fermion parity operator in this way. So it's just a product over all the Majorana operators of our chain. And we can group them in this particular way. Okay, so this is alpha 1. This is beta 1. This is alpha 2, beta 2, and so forth. So we can write the fermion parity operator as I alpha 1 times the product of the pair beta 1 times alpha 2 times the pair beta 2 times alpha 3, and so on and so forth. Okay, so now we see that a beta 1 and alpha 2 are actually coupled by the Hamiltonian, which forces them to forces their product to be say plus 1. Okay, so this in the ground state is say plus 1, and similarly this is plus 1, and so on and so forth. There are only two Majorana operators which don't appear in the Hamiltonian at all, which are alpha 1 and beta n, the first alpha and the last beta. So this implies that in the ground state manifold, or the low energy subspace of our system, which is associated with the edges, we can rewrite our symmetry operator, the fermion parity, in terms of a product of two operators, one of them living in the left edge and the other one living in the right edge. This is actually a general phenomenon. Whenever we have a one-dimensional system that has a symmetry, and it's a gapped system, the bulk is gapped, the low energy states are only coming from the boundaries, we should always be able to write our symmetry operator, any symmetry operator, in terms of a product of two operators, one acting only on the low energy degrees of freedom that live on the left edge, and the other one in terms of degrees of freedom of the right edge. Okay, so the last equality here is correct only as long as we restrict our attention to the low energy subspace of the system, which is associated with the edge degrees of freedom. Okay, but now we see something interesting. So we've written the fermion parity, global fermion parity operator in terms of the product of these two left and right edge operators, in this case just alpha 1 and beta n. But these two edge operators anti-commute with each other. Okay, why do they anti-commute with each other? You can see it directly from here. Okay, alpha 1 and beta n are both fermionic operators. So they anti-commute. And one can show that there are two options here. The two edge operators that represent the action of the symmetry in the low energy subspace can either commute or anti-commute. No other options. So again, we have a quantized index that corresponds to the properties of the edges. This is an anomaly in the sense that realizing such action of the symmetry on the edges can only be possible if our degrees of freedom are living at the boundary of a one-dimensional system. This can never occur if our system is zero-dimensional. If our system was just a quantum dot, okay, with some number of sites, this quantum dot would just have one fermion parity operator, which contains an even number of fermionic operators. Okay, and that means that it would commute with the fermion parity operator of any other fermionic system. Okay, so the fact that these two edge operators anti-commute captures the anomaly of the edge states in the case of the Kitaev chain. So this is yet another way to capture the anomaly. Right, so in this particular case, at the two edges of the system, the symmetry, the fermion parity symmetry, acts in a anomalous way. And this implies that the topological phase of the Kitaev chain is protected in the case, even in the presence of interactions. Okay, so finally, we're going to discuss cases where the interactions actually modify the topological classification of the bulk in a fundamental way. This goes under the name of the breakdown of the topological classification due to interactions. Okay, so it turns out that there are cases in the periodic table where the interaction actually shatter the distinction between different topological phases that would otherwise be distinct. Okay, and we'll focus on one particular example, which was actually the first that was discovered of this phenomenon. And this is a class BD1 in one spatial dimension. And in the non-interacting case, we've actually analyzed this symmetry class before. And this is classified by an integer-valued invariant. So for any integer, there's a distinct topological phase. Okay, so again, class BD1 in one spatial dimension. So we're dealing with a one-dimensional superconductor that has time reversal that squares to +1 and also particle Hall symmetry that squares to +1. Okay, so the Kitaev chain that we've treated before is actually an example of such a phase. So let's consider how in particular, how time reversal symmetry acts on the Majorana operators of this Hamiltonian. Okay, so here's our chain again. Every site has two Majorana operators, alpha and beta. And we can define the transformation law of alpha and beta under time reversal in this way. Okay, so time reversal sends alpha I back to alpha I, and it sends beta I to minus beta I. Okay, and then we can easily show that a term like this, so the term I alpha I beta I, is even under time reversal symmetry, and that's because there's one minus sign because of the I here, and there's another minus sign that comes from the beta. Okay, so overall this term is time reversal invariant. Similarly, any term that couples an alpha to a beta anywhere in the chain would be time reversal symmetric. In contrast, a term that would couple alpha to alpha or beta to beta would break time reversal symmetry. Okay, so now we'll generalize this problem. We'll add more degrees of freedom and also potentially add quartic and higher order terms that describe interactions between electrons along this chain and ask what happens to the classification of topological phases. So first of all, without interactions. It's actually quite easy to see that in class BD1 in one dimension, the non-interacting classification is Z. We've seen it before by the bulk invariant, but now we can see it also through properties of the edge. So first of all, let's construct a phase which has an integer invariant nu in class BD1. This we do simply by replicating the Kitaev chain nu times. Each one of these chains would have its own Majorana zero mode. On the left side, these would all be of the alpha type. Call them alpha 1, alpha 2, and so forth all the way up to alpha nu. Now the claim is that as long as we allow only for quadratic couplings, we cannot actually lift the degeneracy of these new zero modes. Why is that? The only quadratic term that we can write is of the form I times alpha j, and that term is time reversal odd. For example, suppose we try to add the term that couples 1 and 2, so I times alpha 1 times alpha 2. Under time reversal symmetry, as we saw before, both of the alphas go back to themselves, but the I changes sign. So this term is time reversal odd. So this indicates that all of our new zero modes are actually protected and cannot be lifted from zero energy by any local quadratic Hamiltonian. The only way to lift them from zero energy is to close the energy gap and let them couple with the beta zero modes that live on the other side of the system. To conclude, any finite range quadratic Hamiltonian would give us that the zero modes are protected as long as we maintain time reversal symmetry. Okay, so now let's consider the same symmetry class, BD1 in one spatial dimensions, but now let's add interactions to the system. So we start again from the case of a single Kitaev chain. That's the phase that has an integer invariant of 1, and it has just one zero mode at every end of the system. And we should ask, if we add arbitrary interactions, can we lift this degeneracy associated with the zero mode? And because we only have one Majorana operators at every end, there's basically no interaction, local interaction close to the edge that we can add that would change the degeneracy of the system. Okay, so the phase with nu equals 1 is protected, even in the presence of electron-electron interactions. What about the phase nu equals 2? So we know how to construct such a phase. We just start from two copies of our Kitaev chain. Each copy has its own Majorana zero mode. In the left edge, there are two alphas, alpha 1 and alpha 2. In the right edge, there are two betas, beta 1 and beta 2. Okay, and we add interactions to the system and ask, can we get rid of these zero modes at the edges? But as long as we don't close the bulk gap, the only local action of the Hamiltonian at the edge has to be basically of the form I alpha 1 alpha 2 at the left edge, and similarly beta 1 beta 2 on the right edge. But we already saw that this term is time reversal symmetry odd. Okay, so this term is forbidden, and there's basically no other term we can write, even if we allow for a quadratic and higher operators. As long as our terms are all local in real space, okay, they can couple the alpha 1 and alpha 2 to gap the degrees of freedom of the bulk nearby, but that's not going to change the degeneracy of the ground state, which is coming from the edge. Okay, this is just going to renormalize the Hamiltonian slightly and redefine the operators alpha 1 and alpha 2. Namely, the low energy effective Hamiltonian has to be of this form, or just 0, which is what it would be. Okay, so the phase with nu equals 2 is also protected, even in the presence of electron-electron interactions. Now, the phase with nu equals 3 is similarly protected, similarly to the phase with nu equals 1. So let's jump directly to nu equals 4. Okay, so now we have 4 copies of our Kitaev chain. The left edge has 4 Majorana operators, alpha 1 through alpha 4. And we ask what kind of low energy Hamiltonian can act on the left edge, and can that Hamiltonian actually lift the ground state degeneracy. Okay, and there's basically only one Hamiltonian, which is quartic, that we can write, which is time reversal even, and therefore allowed by the symmetries of the system. And this is this Hamiltonian. Okay, it has some amplitude v times the product of all 4 Majorana operators on the left edge. Okay, so such a Hamiltonian is time reversal even. We can write a similar Hamiltonian for the right edge. And we can ask, once we add this Hamiltonian, have we lifted the ground state degeneracy completely or not? Okay, and it's a straightforward exercise to diagonalize this Hamiltonian. Our low energy Hilbert space of the left edge has 4 Majorana operators. Therefore, it's composed of basically 2 complex fermions, or it has 2 to the power 2 ground states. So this is essentially this is a 4x4 matrix, and it's easy to diagonalize. I'll just draw the spectrum over here. So it turns out that the spectrum of the system is still composed of 2 pairs of degenerate states, which are lifted from each other by an energy of twice v. Okay, so this term lifted part of the ground state degeneracy of the non-interacting system, but hasn't lifted it completely. The fact that there are still 2 protected zero modes at every edge implies that the bulk is actually still topologically distinct from vacuum. Okay, so finally, let's jump to the case nu equals 8. Okay, and in this case, it turns out that the interactions can actually lift the ground state degeneracy associated with the edge completely, and therefore the phase nu equals 8 has the same edge spectrum as vacuum, and indeed this phase is actually, in the presence of interactions, is actually equivalent to the vacuum. Okay, so here's an explicit construction to show that the phase with a topological invariant nu equals 8 we can think about as 4 copies of the Kitaev chain. It has 8 Majorana 0 modes at the left side, the left edge, alpha 1 through alpha 8. Okay, and we can write an explicit Hamiltonian which is acting only in the vicinity of the left edge, coupling the edge degree of freedom, namely coupling alpha 1 through alpha 8, and this Hamiltonian, we can show, actually lifts the ground state degeneracy of the left edge completely. So here's the Hamiltonian. It has 3 terms overall, minus V1 times alpha 1 through alpha 4, and alpha 5 through alpha 8. And there's a third term, which is alpha, all the odd alphas, alpha 1, alpha 3, alpha 5, alpha 7. Okay, and let's choose both of these parameters in the Hamiltonian, V1 and V2, to be positive. Okay, I'll leave the diagonalization of this Hamiltonian as an exercise. I'll just point out that it's constructed to be easy because all of these terms commute with each other. Okay, so they're not hard to diagonalize. We can just diagonalize each one of them separately and then add the energies and count the ground state degeneracies. Okay, so it turns out that this Hamiltonian actually has a unique ground state, no ground state degeneracy, and it has a ground state energy of minus 2 times V1 minus V2. And we can actually write down explicitly what's the ground state wave function of this Hamiltonian. There's only one ground state. Now, this ground state is written in a particular basis, so we can choose a basis, say, of eigenstates of alpha 1, I times alpha 1, alpha 2, which is either plus or minus 1. That's this first bit. And similarly, the second bit is I times alpha 3 times alpha 4, and I times alpha 5 times alpha 6, and so forth. Okay, so every state in the Hilbert space can be written as a combination of 4 bits, either plus or minus 1. And this particular superposition, the state with all pluses, all plus ones, and all minus ones, that's the ground state of this Hamiltonian. This you can check explicitly. Okay, so the fact that by only adding local interactions at the edge, we can lift the ground state degeneracy completely, implies that, in fact, this phase nu equals 8, in the presence of interactions, is actually equivalent to the vacuum or to the trivial phase. And this wasn't the case without interactions. Okay, so this phenomenon is the so-called phase collapse. Okay, so this means that we had some different phases of quadratic Hamiltonians that were distinct as in the presence of a given symmetry, even for arbitrary quadratic Hamiltonians. So in this case, the classification of phases in the presence of interactions gets modified from an integer valued invariant to an integer mod 8. This means that any phase that has a topological invariant nu in the non-interacting case is equivalent to a phase that has an invariant nu plus 8, or any multiple of 8, once interactions are included. Okay, so now where does this number 8 actually come from in the interacting phase? There are only 8 distinct phases. Where does the number 8 come from? One can actually understand that quite simply by considering the anomalies of the edge in the presence of interactions. So let's consider again the symmetries of the problem in class BD1. So there are 2 symmetries. There's the Fermion parity symmetry, which is always there. So we argued that in general, whenever we have a bulk symmetry of a gapped phase, we can represent that symmetry on the ground state manifold as acting as a product of 2 operators, one acting on the left edge and the other one acting on the right edge. So that we decompose the fermion parity operator PF into a product PL times PR. Similarly, there's another symmetry to the system. There's time reversal symmetry in class BD1, and we can also decompose or fractionalize time reversal in an analogous way. Now, time reversal is an anti-unitary operator, and this implies that we can write the action of time reversal as a unitary acting on the left, TL, times another unitary acting on the right, times complex conjugation. Okay, and this again encodes the fact that the low energy degrees of freedom are living only close to the boundaries. So now, there are different relations these operators P, R, and L and T, R, and L can satisfy. Okay, so first of all, as we saw before, PL and PR can either commute or anti-commute. So that's one bit or one binary index, nu1, that can be either 0 or 1. Okay, so 0 corresponds to PL and PR commuting, 1 corresponding to them anti-commuting. In the same way, the operators PL and TL on one edge of the system can either commute or anti-commute with each other. That corresponds to a second bit, nu2. And finally, if we look at the square of the time reversal operator acting on the left edge of the system, that's TL times complex conjugation, time reversal, as usual, can only square to two numbers. It can either square to +1 or to -1. So the global time reversal on the entire system squares always, in this case, to +1. Okay, so in the BD1 case, it always squares to +1. But that doesn't mean that the individual time reversal operators that act only on the left and right edges have to square to +1. They can both square to -1, and therefore the global time reversal squares to +1. Okay, so overall we have 3 bits, nu1, nu2, and nu3. Okay, and each one of these indices can be either 0 or 1. Overall, that means that we have 8 distinct phases. Now, it turns out that if we stack 2 of these phases together, their indices add according to the Z8 group. That's not obvious from this, but that's nevertheless true, and that's derived in these papers over here. Okay, so going back to the periodic table of topological insulators and superconductors, the periodic table holds for quadratic or non-interacting Hamiltonians. It turns out that this phenomenon of phase collapse is more general. Okay, so it turns out that for any odd-dimensional system with a chiral symmetry, a similar phenomenon occurs. Okay, so there's a phase collapse, meaning that in the presence of interactions, the topological classification is reduced from an integer invariant Z to a smaller group Zn. And what is n depends on the particular symmetry class. Okay, so it happens not only in class BD1 in one dimension, at every odd-dimensional chiral class, meaning that there is a chiral symmetry, the non-interacting invariant is Z, and the interacting invariant is lower. Okay, it's a smaller group, and this interesting fact is derived in these 3 papers, where there's also an explicit formula for this reduced group N. So let's summarize. Okay, so what we discussed in this video was the effects of interactions on the non-interacting classification of topological phases of superconductors and insulators. So we saw before this a periodic table in the non-interacting case. We argued that whenever one of these phases has an anomalous edge state, then we know that, the classification of that symmetry class has to remain even in the presence of interactions. Whenever the bulk has a quantized response of some sort, which can be defined in terms of the many-body ground state, that classification cannot be modified in the presence of interactions. But there are interesting examples where we neither have an anomalous edge state, which is well defined in the presence of interactions, nor do we have a quantized response of the bulk. And in these cases, the interactions can actually modify the classification in a fundamental way, giving rise to a new classification. And finally, as we mentioned at the beginning, there are other phases that are even not in this table, which are topologically ordered phases that can only be accessed in the presence of interactions. Thank you very much.